All right, welcome everybody. Welcome to our presentation for MagicMeds for Senior Design 2. My name is Nestor Vallejos from Group 18. I am computer engineer.
My name is Eduardo Noguera, and I'm also a computer engineer.
My name is Dakota Bredeker Downing, and I'm also a computer engineer.
My name is Stephen Hudson, and I am also a computer engineer.
All right. So for our project, we wanted to focus on ease accessibility of all items, supplements, and prescriptions. We want to make sure that our device can connect to a smartphone and be able to control it from the mobile application. This will allow us to schedule what we need for our medications and when it should be dispensed from the machine. We will also have notifications to have it notify you of when the pills are going to be dispensed. The device will also have a GUI display that will show what your medications currently are and what they will be in the future and any other updates that needed. The LCD screen also displays pills that will be dispensed, like I said, up until the next day. Some of the motivations that inspired us to do this project was to get the support, to get people support the need to be taking medications, especially with the older crowd, the ones who have difficult illnesses such as Alzheimer's and illnesses that renders them to be able to remember to take their medication. So with our application, we'll be able to send them notifications and stuff to remind them. We want to also be able to have a successful prototype that can be used for future projects. Another interesting fact was that from the CDC, there has been 30 to 50% of chronic diseases, treatment failures, and there's about 125,000 deaths per year in this country for missing your medication. Our goals and objectives were to provide a quality product for our users to help them remember to, like I said, take their medications and also be able to sort them as easily and painless as possible. We are striving to improve the safety of other automatic pill dispensers. We want to be able to have a viable and user-friendly pill dispenser that will simplify the lives of our elderly and anybody else who wants to take pills, such as supplements, medications, and other things. We want to take away the stress of worrying to have to remember medication. So now you could just have it in your mobile device and you'll get notifications to do as such. We want to also learn new skills and technologies, make sure our product is attractive and competitive to other similar products, make it affordable, and have constant communication between the device and your phone. Some of the specification requirements that we wanted was to be able to have it compact and portable so you can move it around anywhere we need to. The device is lightweight, is no more than 3 pounds. Our device will consume no more than 5 volts of power. The device should cost no more than $400 total. The LCD screen will be no bigger than 5 inches across for displaying the information to the user. It will be very friendly and they'll have access to their medications and refills and changes. Quick architecture diagram. The hub of our project is based off the Raspberry Pi. The Raspberry Pi controls the HDMI decoder, which displays information to the LCD screen, is connected to the PCB, which is also controlling the servo motor. Our mobile app will contact a web server and the Raspberry Pi will always be pulling from the web server constantly to ensure that our LCD is constantly updated. Once you are on the mobile app UI, this is the user experience flowchart. We have the sign up page, we have the login page, and once we have the main page, you have the ability to add caregivers, medication, you can see the pages, and you can add or delete as such. So on to Stephen for the software design.
Hello, my name is Stephen, and we will be discussing the software design of this project today. The software was a large chunk of this project, and we can kind of break down the software into 4 different parts. There's the mobile app, there was a caregiver website, there was the GUI on the Raspberry Pi along with the scheduling there, and there was also the code on the microcontroller. So moving into the mobile app, the mobile app was built on a MERN stack. The MERN stack is MongoDB for the database, Express.js, React, React Native, and Node.js. So the whole idea behind the mobile app was a basic account-based application where users could go sign up, schedule their medications, and add caregivers. This way, they can receive notifications when their pills drop. And they can also add that second layer of responsibility there with the caregiver notifications so that the caregiver can follow up and make sure that the user takes their pills. So we'll move right into the sign up page here. Signing up is obviously where a new user starts. It's a very user-friendly process. There's a first name, last name, username, password, email, and a product code. The product code is a unique ID that hypothetically would be assigned to each pill dispenser machine in the market. And this product key is how the machine can identify who the user is and pull their pill information and then start scheduling pill drops. Adding medications is super user-friendly in the app. When you log into the page, this is what you see. You can add medications and you can add caregivers. You can see on the bottom there, we have a bottom navigation bar, a simple 2-page main UI. So here you can see when you add medications, the date of the medication, or the day the medication is taken and the time the medication is taken is added to the page, as well as the name. You simply enter the medication name, the day the medication is taken, and the time, and it adds the medication. Now, if you have 2 medications that you are attempting to add for the same day, it must be added for the same time. Otherwise, you will receive an error since we are only performing 1 pill drop per day. Onto the database. The database is a MongoDB collection. It's a pretty simple one at that. There's about 4 clusters. We have the available caregivers, the caregivers, the medications, and the users. The available caregivers clusters, those that have signed up on the caregiver portal, which we'll talk about later. The caregivers cluster is all of the caregivers that have been added into the app. The medications is all the medications added in the app, and the users is obviously the users that have signed up, and everything is connected via IDs. MongoDB was kind of an obvious choice for our database, as it's simple, everything's laid out in documents, and makes for easy querying. Both caregivers and medication store a unique user ID so that we can easily identify who the caregiver or medication belongs to. Adding caregivers is very similar to adding a medication. You simply hit that big button at the top that says add caregiver, put in a first name, last name, and phone number, and then hit to add the caregiver. And you'll receive this success message here if the caregiver is available to be added. Now, if the caregiver is not available to be added, it means they haven't signed up through the caregiver website yet. The caregiver website allows us to make sure that we are in line with FCC regulations for SMS text messages, and that way you can't just come into the app, add any phone number you want, and have them start receiving SMS text messages. So if they're not in the caregiver pool, you'll see this message show up when you try to add them that the caregiver does not exist. Once the caregiver is successfully added and a medication time is reached, the pills drop and the caregiver will receive a text message asking them to follow up with the user to ensure they've taken their pills. So here is that caregiver website portal where any caregiver can come and sign up to add themselves to that database. Here you can see FCC regulations state users cannot receive SMS texts unless they have opted in specifically to receive the text. So this was just kind of an extra layer that we kind of added on top for from a, I guess, a marketability standpoint, and ensuring that we're within the guidelines and ensure that we're not spamming users with text messages. So on to the LCD display. The LCD display on the device itself has a GUI that will display the pill schedule for the user. What you see here is functionality that we built out in the code for the Raspberry Pi. It was built on Python using tkinter. However, this screen is no longer implemented into our final design due to touchscreen issue functionalities. We had a problem with the touchscreen where it was working and then it wasn't working. So we had to remove the touchscreen. We had to remove the touch-enabled portion of the code, and instead we went with just the screen that you'll see here on the next slide. However, all of this GUI code is done in Python and held on the Raspberry Pi using the tkinter Python library. So here you're seeing the pill schedule that the user will see when they boot into the device. Like I said, the touchscreen functionality is no longer working in our final design. However, you can see here that we have the pill schedule for the user that constantly updates. It runs in a loop, the GUI. So the GUI runs in a loop and constantly reaches out to the database to make sure that it has all the proper information. And if medication is added, then it displays right here on this GUI. Job scheduling. So along with the GUI running on the Raspberry Pi, we also have another Python script running on the Pi that does job scheduling. And we have it set up for every second right now. It reaches out to the database, gets the medication time, gets the current device's time, compares the times, and checks if they match. If the times match for that user, then, or for that product code, I should say, then it will fire off a signal to the app Mega to begin motor movement, and it'll move the motor to drop the current day's pills. Everything is through Wi-Fi. We did not go with a Bluetooth route of any sort, so everything's a wireless connection. We're hosting the app and the caregiver site through Heroku. We use the PyMongo library on the Raspberry Pi for the DB connection between the Raspberry Pi and our database. For the mobile app, we use Express to connect to the Mongo collection, and we're just wirelessly pulling our data back and forth. Any API calls that we needed handled are sending data through JSON, and we tested these API calls using the advanced REST client. For hosting, we used Heroku because it was free, but however, we had some challenges with the free tier, so we upgraded to the $7 hobby tier. All version control is done through GitHub. We have 4 repos holding code, 1 for the mobile app, 1 for the GUI and scheduling, 1 for the caregiver website, and 1 for the app Mega. Our SMS provider is Twilio. We initially were going to use just email addresses and send text message notifications by using each cell provider's email address. However, it was very unreliable. So because of this, we decided to opt for something paid, which was Twilio. However, Twilio offers a free trial, so we actually were able to use it for free. I'm now going to hand it over to Eddie, who's going to discuss some of the hardware and communication aspects over the wires.
All right, so on to the communication. So I'm going to talk about how the Raspberry Pi communicates with the AppMega. So the way it starts is basically the Raspberry Pi sends SPI signals to the Atmega 328. And then as soon as we do that, we try to place the MISO and MOSI pins and route them directly into the actual pins that correspond with the Atmega. So then upon doing that, we actually utilize the SpyDev Python library in order to like actually program it properly and make sure that it was receiving bytes through that communication. Now onto the hardware design. So for the display, we chose an 800 by 480 touchscreen display where the GUI is going to be displayed and then the display is going to be on the device. So for the display architecture, it's essentially we had an HDMI decoder connected to the Raspberry Pi, and that HDMI decoder is connected to that display. And we chose the NEMA 14 stepper motor to have to rotate the pill container and essentially be able to receive the signals from the MCU. So the microcontroller unit is the Atmega 328, and it has a RISC architecture and it has the options to use either I2C or SPI communication. The Raspberry Pi we were able to convert the signals from the Raspberry Pi to the MCU via SPI, and then from the MCU sends instructions directly to a stepper driver that we begin to show in the next slide. So in the Raspberry Pi's focus is basically to just be able to have interactions between to be able to program the MCU and have the interactions be constant and ensuring that all the communications are running according to how we program the MCU. So then the control signals between the MCU and the LCD ultimately make it easier to have everything displayed at the right time and everything synchronized in the right moments. So there's constant database communication through the Raspberry Pi using its Wi-Fi capabilities. So for our PCB has a 5-volt input connectivity, and those 5 volts get sent straight into the MCU, and then the MCU also gets is able to communicate to our TB6612 driver, and then from that driver it sends straight into the 5 pin port header that's over here. And so our PCB has a combination of surface mount and through-hole components. All these in connection ultimately sum up how our PCB is able to function properly. So onto the PCB schematic. So this PCB schematic again shows how we have connected the 5 volts into the MCU, and then the MCU, how we routed the analog pins straight into the TB66 stepper driver. And as included in there, we have all the headers that correspond to the proper communications. And we also have a header that corresponds to the MISO and MOSI connectivity that's needed in order to send data between the MCU and the driver so that it can function properly. So the most important thing to take into consideration is that we also had a 60 megahertz clock, which allows for the data to be communicated at a specific frequency, and so that the driver can be able to rotate the motor at the proper time. So I will pass it now to Dakota for the container design.
Hello, everyone. Basically, our container design was 3D printed. It consists of 3 main components: the hardware container, the medicine cup, and the pill wheel. These parts were created in Fusion 360, and they were exported through STL files. From there, they were sliced into GC code or G code using Cura. Once sliced, the G code files were put onto the 3D printer and the Ender Pro and printed it. Basically, our design was to have a container to hold the electrical components, a front cut screen area to put the touch screen on for the users to see, and a hole in the top to put the cap on with the pill containers inside it. If you go to the next slide, I can show the rest of it. All right, and then the rest of it is just the pill funnel, so that when we used gravity to allow the pills to fall into this funnel, and then it'll funnel into this medicine cup. Like I said, all the components are 3D printed. The pill wheel body is designed as a pizza cutter pill dispenser. So we have 7 sections for every day of the week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And then we have one dud, which is a fully solid piece. And then there's this disc, which is the pill wheel cover that goes on top of it. Now the pill wheel cover disc sits on top of the dud for the starting of the week. And then when it begins to rotate to dispense the pills, it'll go over the pills to allow the pills to fall through that hole that you see there into our funnel. As you can see, this is basically our rough design from the beginning. We made sure that the cylinder was 3D printed. Obviously, the front was to hold the LCD screen, 7-day pill wheel, one with a dud, so that it can start on Monday once it starts to rotate. The motor will hang upside down, so gravity will have effect. And then we had walls printed to force the funneling to force the pills when they fall to funnel into the pill to funnel into the funnel bed. And then here's an administrative content. Basically, I'm going to go over like our roles. Steven basically obviously did most of the mobile application, and he helped me with designing the hardware, out casing. I did the casing and worked on the power distribution. Nestor worked on the embedded applications in power, and Eduardo worked on embedded and power as well. Our budget and financing, obviously, we're not a sponsored group. This is all over pocket. And while starting of COVID, we came into our design. We wanted to make it as inexpensive as possible because obviously none of us have cash like that. And, you know, we're all college students, so it's a little rough out here in these streets. Basically, we financed it and made it so where the bill of materials, like all the materials we bought were cheap and obviously usable to the highest extent to give a quality product. We approximately totaled our bill of materials to $246. Our main budget was $500, so we hit well under, which was great. And then here's our bill of materials on a spreadsheet and from the PCB. As you can see, the total was $246 out of $500. And then we ran into a few design issues during this whole project. We ran into the issue of where the Python code for the GUI would not update the pill on the touchscreen. That is now fixed though. It works perfectly well. The touchscreen stopped working, like Stephen mentioned, so we had to remove that type of formality. And then we ran into the issue of problems with states with users. So if you would sign into one user and then you have their stuff and you sign out of it and try to sign into another one, sometimes it would give the other user's info to this user. That has been fixed though. Stephen did a great job at fixing it, thank God. Shout out to him. The PCB prototype was not fulfilling our desires when we first bought it, so we had to go through 2 revisions to make it work properly with our equipment. When we were hosting the website and stuff, we were using Heroku, but we were using the free tier at the time, which made it really, really slow because, you know, nothing comes good free. So, so we had to invest into the $7 a month one to make it more efficient and more usable for testing. The first LCD screen we got was cracked, so we had to buy a new one. The printing for our cases take forever. One of the prints took at least 26 hours. Another one took another 24 hours. As you can tell, it's a long time. The PCB burned. The bootloader and the programming had issues. Loading the pills in the wheel were an issue because of the hinge mechanism, but we fixed it just by taking the cap out first and then moving it with the hinges. And then when we first tested it with gravity, we didn't think we needed a funnel at first, so we tried it, and then we realized that pills go everywhere, including into our electronic portion of the device. So we invented the funnel to make it more easily accessible to go into the cup. Any questions?